So for this next one, transformations chapter review, what we have is we've stopped using the word symmetry in Common Core. Basically, they've replaced it with map onto itself. Now, to explain that really quick, basically you have to be able to do something such as a line reflection or a rotation um, where the figure will cover basically the same outline. So think map onto itself. It means it's going to, we're going to cover the same outline. After either a line reflection or a rotation of some kind. Okay? So, translation obviously cannot do that because every point will move. So a real simple one is, let's talk about a rectangle just for a minute. Okay? If we line reflect, well, that was a bad one. If we line reflect over that line, what's going to happen is this point, we'll call it A, will end up mapping onto B. Okay? Now, obviously, A prime, it doesn't land back on itself in the exact same location, but it lands on something on the other side that it has a match with. B and A will basically switch spots. Same with this point right here on the figure. Okay? If we call that C and D, C and D will switch locations. But every point on one side has a match on the other. That gives us um, line symmetry, okay, or a line reflection that would map it onto itself. Now we got to be careful with a rectangle. This is important, something I said in the class. Basically, a rectangle can have a side that's 10 and another side that's 5. Sorry. So what would happen if we try to reflect over this line? It looks like, it looks like there's a line of symmetry there. Really convincing. However, here's how you can tell it's not going to work. Because you would basically have to have this side right here land on this side, but that can't happen because this side has 10 and this side's only 5. So even if the angle was good, which it's not, by the way, even if the angle would work, you'd end up being down here somewhere too far. And there's more to it. Okay, the angle would be a little bit smaller to actually land over there somewhere. So it's just not going to work. Okay, so a rectangle will have 2 lines of symmetry. That's pretty obvious. You wonder about the diagonal. It doesn't work unless it's a square, you know. So that's something for line reflections. Rotational symmetry, please just relate it to a circle. It's so much easier. Think of it as someplace on a circle. So when we do this problem right here, 5 equally spaced dots in this star, essentially. Okay? And the center of rotation is the center of the circle. Okay? I don't know how to get this, but I'll try. All right, this is going to be pretty bad. I'm sorry. That's not as bad as I thought it was going to be, but basically what you think of is for rotational symmetry, there's 360 degrees to go around a circle. What you're going to want to do is divide it by however many equally spaced points there is. In this case, it's going to be 5. And that is going to give us 72. So every 72 degrees, we're going to end up landing back on the same outline. Okay? Obviously, point A is going to travel to point B. They're going to switch locations. B is going to land on C, so forth. But what we do is we cover the same outline. Okay? So let's go in, after that quick lesson, let's go and look at 13A. All the lines of reflection for this star. You're going to get 1 through every vertex, assuming, of course, all the sides and angles are identical, which they look like it. We'll make that assumption right now. So those are all your lines of symmetry. Okay? That, of course, is going to be the center for your rotational symmetry, and we took care of the smallest angle, and that's the work for that. So this is the work for part C. That point P is the answer for part B, center of rotational symmetry. And of course for A, we got all those lines. Okay, so we answered all 3 parts. Sketch and label a rectangle and its image after the reflection in a vertical line below. Just make it easy on yourself. Try to make it so that it is already, tipped perpendicular is the best way to go. Sketch. Here's the nice thing about sketch. Sketch implies you do not have to be perfect. So you don't have to use the compass tool. Use a straight edge, but we don't have to use a compass tool and, draw those circles. And it does, like I said, it just doesn't have to be perfect. So just perform it. Here's ABC. All they want to know is, do you realize it's got to be about the same distance away? Okay. You should keep it about the same size, as close as you can. Really all we're looking for is, does the student essentially switch the orientation? Do they recognize C to C prime as perpendicular and the same distance away? That's all. Okay, we're just trying to find out for that. Which of the following are preserved? Now, parallelism, here's that. We didn't talk about it much at all in our class, but parallelism, if 2 sides are parallel, in the pre-image, are they still parallel in the image? The answer is yes. So that's not going to change. The only, maybe a stretch would change parallelism, but I don't think so. I think if 2 things are parallel, even a stretch won't mess that up. Now, perpendicularity, I could be wrong about the stretch, but parallelism is going to be preserved in all the ones we do. Okay, perpendicularity, that's also going to be preserved no matter what we study. We don't study stretches. We just know they exist in this course. So that could be ruined by a stretch, but nothing that we do. So we're always going to preserve these. Orientation, that is not preserved. Okay, we know that for a line reflection. Now distance is, this is tricky. It's up in the air between even the teachers. I'm looking at distance is the length of these sides. Okay, the distance of those sides. Now the distance they moved is different, but we're going to say, let's just agree right now, the distance of corresponding sides. So corresponding side length, if this is what they mean, then it is preserved. Distance the points moved, not preserved. So that could be an indication between a translation versus anything else. But let's just say they mean corresponding side length. Angle measure is always preserved in everything we do, again, except possibly a stretch. Area is always going to be preserved until we go for dilation. All right? So those are some good ones there. How would you draw this to make sure there was an invariant point? Really simple. I would put a side right on there. Now this is going to give us a bunch of invariant points. All the points along BC are going to be invariant now. So it's a lot easier to talk about it when I actually sketch it. Okay? Make sure some points, at least one point, on ABCD is on the mirror or line of reflection. Okay, sketch and label a rectangle and its image. Sketch, again, is a little more relaxed. It's not perfect. They just want to know, here we go, right there. A southeast direction, okay, that's pretty mean. So this is east, this is south, if we agree here that the compass looks like this. Southeast would be in that direction. So let's try to move in that direction here, okay? let's go, that looks decent, right? So we'll call this A, B, C, D, A prime, B prime, C prime, D prime. Okay. All right. And they're talking about, this is the vector A to A prime. That looks southeast to me. Which of the following is preserved? Everything is going to be preserved. So parallelism, perpendicularity, orientation, distance, angle, measure, and area. All those things are preserved with translations. One thing that's missing is slope. Slope is also preserved in translations. How could you draw this to make sure there was an invariant point? We can't unless the translation vector is 0, which means nothing moves. Distance is 0, means nothing moves. Okay? Every point moves the same amount in a translation. In a translation. Okay? That's the only one that has to happen that way. Line reflections, the points can move a different amount. Rotation, same thing. So we've seen that. Translation, everything's going to move the same exact amount. All right, what's the image after reflection over the line x equals 2? No, it's saying, okay, so here's the line x equals 2. Right, move over 2. 5, 1 would be about right there. Maybe too high, but okay, so let's call that A prime. If I was looking for A, it must have been perpendicular, right, this way. So it's going to be somewhere where we don't know the x, but we know the y is going to stay 1. Okay, so perpendicular. Now, same distance away. From 5, 1 to the x equals 2, that's a difference of 3 units. So let's move 3 units this way, and we're going to hit at -1. So that's going to be the pre-image. A is going to be at -1, 1. And we'll pick it up from here on the next video. Thanks so much.